Hello! In this video, we're going to go over this week's worth of goodness, sections 1.4 and 2.1. Well, to be very honest with you, in section 1.4, there's really not much to lecture on. It's just a bunch of examples. In fact, I'm going to pull this over here so I know what videos for you to watch. The purpose of 1.4 is to be able to look at a graph and extrapolate or extract information from it. Something you can safely say with the information you're given. You will need a calculator, but you're not going to do anything crazy, just basic arithmetic as you have been doing so far. So for section 1.4, please watch videos 10, 11, 12. Again, not much, let me double check, not much lecture at all. If I was in class, I would just be saying, hey, let's do these videos. Yep, that's correct. All right, so please pause this one and watch 10, 11, 12, and that'll get you through section 1.4. The remainder part of the video is section 2.1. All right, now let's talk about section 2.1. Symbols and terminology. So we move away with playing with numbers and inductive reasoning. Well, not too much. I mean, we still have inductive reasoning for the entire class, but not to the level that we saw in chapter 1. And we now move into what is called set theory. And the idea of set theory is that you have groups of objects and you're going to manipulate them by combining them, seeing what they have in common, taking out things they have in common, and so on. And we're going to do this by writing down elements, and we're also going to do it visually. And there's going to be a bunch of new terms in this chapter, and those same terms will carry over into the next chapter. So this is not one of those things where you can just learn it and forget it. You sort of will need to know this to finish out the next chapter, guaranteed. So there's that. The only difference between the next one and this one is the symbols we use. So you're going to have math notation in this chapter and also in the next one. We start off with the most important definition, and that is the idea of what a set is. And I'm going to attempt to write this neatly. A set is a collection of elements. And we call those elements, oh my gosh, I already messed up. Why? Because it's not supposed to be a collection of elements. It's supposed to be a collection of objects. I'm writing in pen, you say. Sorry. A collection of, I'm not editing this. A collection of objects, and those objects are called elements. There we go. So we have a two terms in one definition. You're welcome. So, for example, a set could be the set of all people at a restaurant at a specific time, and every person in that restaurant would be considered an element of that set. That's an example. It doesn't have to be people. It could be animals, stars, whatever you want to create a set. Now, there are two major ways to write a set, and they're listed below: set builder notation and roster method. We'll start with a set builder notation. In a set builder notation, there's a way you write it, and it's going to be a little bit crazy. Sets are designated with a brace, which is this guy here. So a left brace, that's a left brace because it's on the left-hand side, starts off a set, and a right brace ends the set. Do not call them curly brackets. They get offended. Now, next to that, we pick a variable name. It doesn't matter. You can pick X, which is a generic letter. If your set was all about colors, maybe you can pick the letter C so that it reminds you of the letter colors, or the word colors. That's fine. But X is a generic letter to use. So we next pick a variable name. Then we draw a vertical line. in this chapter, this vertical line means such that. Then we give the property. So we're saying everything that these x's have in common. And then we finish off the set. So let's suppose that we cared about, we wanted to talk about all Cleveland sports teams, because who doesn't? We could say left brace, which would be pronounced the set, and then we can pick a letter here. Since I said Cleveland sports teams, we can say C for Cleveland, that's fine. The set, and this would be pronounced of all C, vertical line, means such that. And then we give the property. Well, we only care about Cleveland sports teams. So we would say C is a Cleveland sports team. And close it off. So then we could talk about only the important Cleveland sports teams, like I think they were called the Strikers and also the Lumberjacks. You know, the ones that won stuff way before it was cool. So this set contains anything that is considered to be a Cleveland sports team. Notice we're not actually saying what those elements are, but we know what the property that contains them are. If we wanted to say what the elements were specifically, that's the roster method. So in a roster method, you list the actual elements. It wasn't the Strikers, it was called the Force. I'm again thinking of Persona 5 Strikers, which comes out next month. What are you going to do? So when you list the actual elements, you may already be familiar with the word roster, especially for sports or also for classes when the teacher has the list of names. And if you actually list them, that's the roster method. If we wanted to list all of them, we could say Cavs, Browns, Lumberjacks, even though they're not around anymore, and I totally forgot who the current AHL hockey team is. That's okay. And then I don't know what the rest of them are. Well, they're not called the Indians. Are they called the Indians anymore? The baseball team. Oh, I went to the next slide. Boop. Well, if I know there's more and I'm just too lazy to list them all, we can put the three dots, the ellipse at the end there, to say, hey, there's more here, and then finish it off with the right brace. Please be careful that what I wrote here is perfectly acceptable for a roster. When you are writing a roster, I would say have at least 3 items before you put the dots at the end. If you just had 1 item, I keep doing that. Why does it do that? And then you put dots, I can't, as a viewer, know exactly what you're talking about. Are you talking about only basketball teams? Are you talking about sports, teams that start with the letter C? Are you talking about, I don't know. Maybe you're talking about Cleveland sports teams, but just with 1 element there, no idea how to generalize the entire group. So you have to be extraordinarily careful. Please at least have 3 elements and then the ... at the end. For other things, you might be able to write them all out, and you just write them all out. You don't need the ... So what just happened was we wrote the exact same set twice. Here we wrote it in set builder notation, and down here we wrote it in roster method. So those both mean the exact same thing, just a different way of writing it. So again, set builder, you're saying what the property is. Roster, you are actually listing the items. Okay, so that brings us to our first example, which is video number 13. So if you would, please watch video 13, and come on back for more 2.1 goodness. Okay, next up, let's talk about some special sets. First off, we'll talk about the null or empty set. The null or empty set, doesn't matter what you call it, is the set that contains no elements. So, as you previously saw in the last video, there was a very true example of the empty set. Because there are no good Vin Diesel movies. We all know this. Other things, for instance, if I said the set of all x such that x is an even and odd number. There is no number that is both even and odd. It can't happen. So there's two ways you can designate this set. You can write braces with nothing in between them, or you could write a circle with a... Ugh, that could have been better. Can I go backwards? I can't go backwards. How do I erase that? I'm so embarrassed. Okay, I'll try that again. Okay. I'm going to do my best. That was better. You can draw a circle with a line through it. 2 comments. 1, never ever in a math class use this to represent 0. If the answer is 0, but you write this, you're saying there is no answer, and it's not the same thing. Well, I do that in my computer science. But we're not in a computer science class, we're in a math class, so there's that. So please be careful with that. Comment number 2, never put the symbols together. This is not the empty set. You sort of want to think of an empty set as a paper bag with nothing in it. So if I gave you a paper bag with nothing in it and I said, what's in it? You'd probably say nothing. Technically there's air and dust, but we won't get into that. But if I put a paper bag inside of a paper bag, this is what that's saying right here. And I said, what's in it? You would say there's a paper bag in there. All right. Well, then that outside bag is no longer empty. So don't combine them. Write either one of these symbols here, but don't put them together. Okay. Next up are some numerical sets that are very important in math. Only the first couple are going to be important for us. You might know about our natural numbers. These are also called the counting numbers. And they are 1, 2, 3, 4, 5. And there's a bunch here, right? So I can put the ... to say, hey, this pattern keeps going. And the viewer should be able to know, okay, I know what comes next, 6, 7, 8, yada, yada. Now, if we included 0 to that set, we get what are called the whole numbers. It may sound strange that adding only one additional number creates a new set, but as it turns out, historically, the number 0 is one of our newer numbers in mathematics, and you have to remember math has been around for a long time. So when I say newer, I mean like hundreds of years ago, maybe thousands. I can't remember. Because numbers used to be used, or only be used, really, to represent things. And if you didn't have a thing, then why represent it? So if you had no sheep, you wouldn't write that down. You would just say, I've got no sheep. So when 0 came about, it wasn't used to the extent as it's used today, meaning like as a placeholder. For instance, in Roman numerals, which we'll learn about later, they had no need for a number 0. It made no sense to them. So there's no need for it, no need to invent a symbol for nothing. So 0, very helpful now. Okay, if we take our whole numbers and also include the negative versions of them, we get what are called the integers. Notice this one has the 3 dots on both sides. Hooray. There is notation for the integers that you may have seen before. Integers can be written or summarized by a double-barred Z. So it is common, I didn't say this before, that we can use capital letters to represent our sets. Like up here, we could say the set N because we talked about numbers. That's fine. The double-barred Z is a specific symbol to represent the integers. The reason that it's a Z is because in German, and this is true, I'm not making this up, the word for integers starts with the letter Z, and a lot of our math comes from Germany and France. So there's influence with the naming convention there. So going back up to the natural numbers, because the natural numbers are just the positive integers, you might see the natural numbers being written as the double-barred Z with a plus sign. I did it again! So Z plus, that sounds French, is the natural numbers. If we take our integers and we put them over each other to create a fraction with a very important restriction, we get the rational numbers. Now watch how the rational numbers are being written. The first 3 there were written in roster notation. We're actually writing out what the elements are. Rational, you can't really write them out adequately in roster notation so the viewer knows exactly what you're talking about. We have to switch to set builder notation. So if you were wondering, well, why use one over the other? This is it. Sometimes you just can't write them out. So rational, the typical letters we use are P and Q. So P over Q, such that P and Q are integers. Now, as I said, there is a very big restriction with rational numbers. What is it? I can't hear you, but hopefully you said Q does not equal 0. You can't divide by 0. Bad things happen if you divide by 0. So anything that has the format of an integer over an integer where that denominator is not 0, we call it a rational number. The symbol we use for a rational number set is a double-barred Q. Great. And now, between the rational numbers, not yet. Not every number, though, can be written as a fraction. That's what a rational number is, a number that can be written as a fraction. Every integer can be written as that integer over 1. So all integers are rational numbers. But not everything can be written as a fraction. So, for instance, square root of 2, 1.4, blah, 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 goes on forever. No repeat, doesn't end. That's considered to be an irrational number. Sorry, my dog is going to town on the toy. It's very squeaky. So another way to say rational is that it can be written as a fraction, or the decimals repeat, or the decimals terminate. Any one of those 3 is perfectly fine to say. Irrational, the decimals don't repeat, don't terminate, would be the best way to say it. So again, in set builder, another way to do it, we can say the set of all x such that x is a non-repeating, non-terminating decimal. Ooh-hoo. So square root of 2 is a good example. Pi is a good example. E, which we'll talk about later, good example. These are all numbers that never, decimals don't repeat, don't ever terminate. Okay. If you put the rationals and the irrationals together, you get the real numbers. So the set of all x such that x is rational or irrational. You may have already seen the symbol we use for R. It's a double-barred R. I'm sorry, the symbol that we use for real, double-barred R. Okay. So those are important numerical sets just to keep in the back of your head. I would say of these, natural whole and integers are going to be the biggest ones for this class. The other ones don't come up too often. But if anything, again, you see 3 good examples of roster and 3 good examples of set builder. Excellent. Okay. Next up, let's start to introduce some big-time notation. First up is cardinality. Cardinality represents the number of elements in a set. So the ones we just did have infinite cardinality because there's infinitely many real numbers, infinitely many integers, so on and so forth. We're mainly going to be sticking with finite sets, which is a fancy term for the cardinality is just going to be a whole number. So for instance, if I had the set A was A, B, C, D, E, and I asked you how many elements are in that set, you would say 5. Notationally, we would say lowercase n, and in parentheses, we'd put the set name is 5. So this would be pronounced the cardinality of set A is 5, or the number of elements in set A is 5. Done. That's all cardinality is, the number of elements in a set. Next up is the idea of is an element of and is not an element of. So using our set A here, I could ask you, is the letter D in the set A? And you would say, hey, yeah, it's right there. So notationally, to say something is inside of a set, we use this symbol. It looks like a C with a line in the middle. So to use it, we would say D is an element of the set A. That's how that would be pronounced. D is an element of the set A. Now what if I asked about the letter F? Is F in the set A? And you would say, no, it's not. Well, anytime in mathematics, usually, if you want to say something isn't something else, you just put a slash through it. So if this is an element of, then this is not an element of. So F is not an element of the set A. That's all that means. I promise. Okay. The last thing before I let you watch, or set you free to watch another video, is the idea of equal. When you are writing sets, especially in roster method, which is going to be what we mainly concern ourselves with, you could rearrange the elements, in any order you want. The order in which you write elements in a set does not matter. So if everything in one set is the same exact stuff in another set, and you can say that in both directions, we say that the two sets are equal. And the symbol we use is just the equal sign. We don't have anything fancy here for equal. But the big takeaway again is you can write sets in any roster method. You could write the elements in any order you want. All right. So with that said, please watch video 14 as he looks in his notes. He looked in his notes. Watch video 14, and that will summarize. That will finish off section 2.1 for you. All right. Have a great day. If it appears that next week I'm wearing the same shirt, it's because I'm going to film it right now. Bye.